Alright, so I ended here in the last video, and if you're just joining us, make sure you watch the previous video that I did while explaining the question 1 and question 2 of this question. So like I promised that in the next video I'm going to complete question 3. So here is it. Okay, now I said that because that video was already a little bit longer. It was around 36 minutes already, so I prefer to complete the question in another video. So in this question 3, we are supposed to find the components perpendicular to AB of the reaction force exerted at the axis. That's what we are doing. So like I said, if you're just joining us and you're able to watch the previous video on this so you don't get lost. Okay, so like I explained, so what we are going to do is that we draw our diagram first. I said it, so I'm just going to edit the diagram you see here. Now there is a reaction at the hinge. The hinge is A because the rod is kind of held at A and then it is released from rest, so it is kind of swinging in that vertical plane. So having that in mind, I'm just going to remove all these distances and then we try to indicate the various forces because there's a reaction there. We try to indicate the various forces that are acting. So there is a reaction at the hinge because it is held at the hinge. Okay, so the reaction at the hinge, you're going to have a reaction force which is perpendicular to the rod. So we have something kind of perpendicular to the rod, and then we also have another reaction force which is in the same direction of the rod, meaning parallel to the rod. The component that is perpendicular to the rod, we call it the transverse component, and the component that is parallel to the rod, we call it the radial component. So in fact, here we are just dealing with the component that is perpendicular to the rod. So we are just going to do that. Okay, now maybe we can call that component, let us give it a name. So since the reaction, let's just say it is RP, meaning arrow perpendicular to the rod. So here is it. Now the next thing to do is that we are going to also indicate the forces that are acting on this rod. We have the weight of the rod. Now we are not going to call these forces separately, we are just going to combine everything, meaning that we are going to combine the weight of the rod alongside the weight of our particle. Okay, so I'm just going to choose any point here. Remember that if the particle was not involved, then the weight of this rod is going to be acting at the center. Okay, but since this particle is involved, it's not going to be acting at the center. So we are going to find the distance from the point A to the center of mass of this system. So let us just say, okay, the center of mass of this system lies maybe at a certain point, and we know that yes, the weight of the system is going to be acting is going to be passing through that point. So let's just put it here for example. Okay, all right, now what's going to be that weight? That weight is going to be the sum of the masses in the system times G. So we have the mass of the rod, which is 4m, plus the mass of the particle, which is 2m. So you have 6m, then times G because we are getting the weight, so 6mg. Okay, now this weight is acting vertically downward and the rod is kind of inclined. It's like an inclined plane. Okay, so we are going to have the component of the weight that is as well perpendicular to the rod, something like this. So this is a component of the weight perpendicular to the rod. So if you resolve carefully, it's going to give you the weight of the rod times cos theta. So we have 6 mg cos theta. So 6 mg cos theta. If we're involved with parallel component, we are going to get 6 mg sine theta. But since we are not interested in that, we just have our component of the weight of the rod of the system actually, which is perpendicular to the rod. So we have something like that. Okay, now the next thing to do is that remember that the angle theta here, let's just indicate the angle for convenience. So here is the angle theta. Alright, now we need to know that this is actually a rotational motion. So we apply the Newton's second law. So applying, because we need that reaction, apply Newton's second law of motion about which axis. Let us be very specific. Let us name the axis that we are applying the Newton's second law about. So let me just say this is the axis that I am applying the Newton's second law about. Let me call the axis let's say it is the axis let's say maybe delta. No, not delta. Let's say axis y. Yes, okay, let's say it's the axis y. About the y-axis, where the y-axis is this axis that I have represented. So applying Newton's second law of motion about the y-axis, what do we know about the axis y? What do we have? We have that the resultant force about that axis is equal to the mass times the acceleration. But this acceleration in this case is actually the tangential acceleration, because it was in rotation. So we have the resultant force. The resultant force in this case is look at the way the body was rotating. It was rotating and going down this way. Okay, so we are going to take the force 6 mg cos theta minus, kind of, this is resistive, minus rp to be equal to 6m times the acceleration, that's Newton's second law of motion. So we have 6 mg cos theta minus that resistive force rp to be equal to the mass of the system 6m times the acceleration in that direction, let's say a y. But what is the acceleration in that direction? So we are going to have our rp, because that's what we are looking for, the component of the reaction force perpendicular to the axis. Okay, so rp is equal to 6 mg cos theta. Oh, sorry about that. So rp is equal to 6 mg cos theta minus 6m times ay. Okay, now what is our ay? Our ay is equal to, now like I said, it is the acceleration in the tangential direction. So it is r, which is, what is this r? This r is the distance of the center of mass of this system from the axis. So let me indicate r for you to see. Let me try to complete, let me try to extend this. Now the r we are talking about is this distance, the distance from the center of mass of the system. So the center of mass of the system is where that weight is, like that. Okay, so something like that. Not drawn to scale, but I'm just trying my best. So we have that distance from the center of mass of the system, though we have to extend it right up till this not, but anyways, that's r. So let me say this is r. So the tangential acceleration is simply that arrow times theta dot dot. So it is arrow times theta dot dot, and theta dot dot is kind of second derivative of our angular displacement. So that's it. Okay, so we we need to get arrow and we need to get theta dot dot. So how do we get arrow? So let me just see here that where that. Okay, now how do we get arrow? We are going to let's see, how can we do to get arrow? Okay, so we are going to use the principle of moment. So since the system is at equilibrium, since the system is in equilibrium, what do we have? We have that the sum of the clockwise moments, so the moment of the individual parts, is equal to the moment of the whole system. The moment of the individual parts, we have the moment of the rod, and we are taking the moment about the axis y. Okay, so the moment of the rod is the mass of the rod 4m times its perpendicular distance from that axis, which is a, because it is simply the weight of the rod, sorry, not the mass, 6 mg, because we take the weight times the perpendicular distance, but the weight itself is 4 mg. Okay, if we come here, we see that the force acting here, let's come back to this. We see that the force acting, the weight of the rod here is simply 4 mg. Okay, 4 mg, and the perpendicular distance from that guy to the axis at A is small a, because it is half of the length of the rod. So we have 4 mg times A plus that of the particle, which is 2 mg, times its perpendicular distance, which is 2a. Then we equate it to the mass of the system, 6 mg, times its perpendicular distance, which is the arrow. Alright, so this means that, in fact, let me just write it here. This means that we can get arrow, because you see that mg, we first of all cancel all through. Mg cancels mg, cancels mg. Left hand side is going to be 4a plus 4a, which is 8a. Right hand side is 6 arrow. So this means that our arrow, is equal to 8a divided by 6, which is 4a divided by 3. Now, how do we get theta dot dot? We proved something in the previous video, that's in the previous question as well. We proved that this guy is equal to this. So if we differentiate with respect to theta again, we are going to have something. So differentiating both sides with respect to theta, we have 5a. Now when we differentiate the theta by dt all squared, we drop down the power, then we differentiate, we drop down the power, we have 2, then we differentiate the theta by dt, it gives us the squared theta by dt squared, and then we multiply it with the theta by dt to the power minus 1, which is 2 minus 1, and 2 minus 1 is simply 1. Okay, so we just have that. Then we equate it to 6g, we differentiate sine theta, we get cos theta. Alright, now this the square theta by dt squared is theta dot dot, because the second derivative of the angular displacement with respect to time. So this therefore means that our arrow p is equal to, because from here we see that let me just say, let us get theta dot dot. Okay, so theta dot dot, I'm just going to write in a short form this time around. Theta dot dot is equal to 6g cos theta, 6g cos theta divided by, let us see what we have. 6g cos theta divided by, we divided by 5a, and also divided by 2, and we also divided by what? Theta by dt. So we have divided by 10a times theta dot. Okay, times theta dot. That's what we have. Okay, so with that said, we have that our arrow p is equal to 6 mg cos theta 6 mg cos theta minus 6m times ay. What is our ay? Our ay is arrow times theta dot. Okay, and our arrow is 4. In fact, we are going to replace that. Our arrow is 4a on 3 times our theta dot is this guy here. We can even simplify. 2 can go here 3 times and 2 can go here 5 times. That's what we have. So we have this. Okay, so that's what we are replacing as that. So we have all of this. So this is going to give us 6 mg cos theta. Now we have 3 here cancels with the 3 here, so this is going to give us 4a. Now what is going to cancel? Our a here, as the a in the denominator here, cancels with this a here. We multiply 6 with 4. What do we get? We get 24. So we have minus 24 mg then cos theta, 24 mg cos theta divided by 5 theta dot, 5 theta dot. Let us see, how are we going to get theta dot? Let us see from where we can get theta dot, because theta dot is our angular displacement. Okay, because from here it's going to be complicated to get theta dot, because clearly our theta dot will give us a square root of all of this, which is a little bit shaking already if we try to replace that with a square root. Alright, so okay, I've seen where we made a mistake. Okay, we differentiated something and we forgot to attach theta dot as well, which is a common mistake that we always make. See, when we differentiate sine theta, we need to attach theta dot. Okay, because this theta here is not in terms of t. So when we differentiate sine theta, we need to attach that we have theta dot, right? Theta by dt. So here is actually cos theta times theta dot that we have to attach there. So cos theta times theta dot, and you see how the theta dot cancels. Okay, so you see that the theta dot on the left hand side here, I'm going to put it in a dark color. We cancel with the theta dot in the right hand side. Okay, so it's needless to put the theta dot here again, so we don't have to put the theta dot there again. So be always vigilant, Okay, so if we simplify this, we are going to get 30 minus 24 is going to give us 6 mg cos theta divided by 5. So that is our component of the reaction that is perpendicular to the plane. So guys, thank you for watching the video. Make sure you like the video as always, subscribe to the channel, turn on your notification, share the video with your friends, with your teachers, with your colleagues as well, provided you're a teacher watching this video. Thank you once more, and see you in the next video.